introduce Lamberto Rondoni, and he will talk about non-equilibrium response, relaxation, and the tea mixing condition.
Yes, thank you very much. And again, like the other speakers, I want to thank the organizers for the invitation. Unfortunately, I could only stay this week, which is the only time when I could get away from my university in Torino. I would have loved to spend longer time here, but anyways, this was already quite nice. And so this talk, I wasn't sure about the audience I would find here, so it's introductory to some issues that are being discussed in non-equilibrium statistical mechanics these days. And you see from the title what it is. I'll go slowly through various issues, which maybe they suggest something to dynamical systems people. Maybe even this morning I saw something that could be vaguely related to some of the things that I'm going to tell. And if there is a vague relation, then looking more deeply, maybe one finds a tighter one. In practice, what I'm going to illustrate is what is called these days the dissipation function. We'll see what it is. It's a function that plays a role in a whole set of developments in the study of non-equilibrium systems. Okay, so I consider it a kind of non-equilibrium thermodynamic potential. I'll try to make more precise what this is. Through this function, we can obtain what are called transient fluctuation relations, which means ratios of probabilities of observables taking opposite values, okay, which is a symmetry of the state in which the system can be found. Transient, this would be the probability measures. Mu 0 is a non-invariant measure. And then there would be what are called steady state fluctuation relations. With the infinity here, I mean that they are invariant, and presumably they are reached in time starting from the non-invariant one by iterating certain dynamics or evolving certain dynamics. I will conclude with what could be the most useful objects for applications in fields in which one is looking at evolution of perturbations or whatever. Okay, evolutions of observables. So what would be a quite general non-equilibrium response formula. Okay, and in doing this, I will encounter the notion of tea mixing, which I'm not sure whether at this point isn't a trivial example of what you were discussing earlier. Okay, we'll see. So this is the setup where these ideas come from. They come from molecular dynamics, where people solve numerically equations of motions for particles that follow some kind of evolution equations, which are summarized here, and in which you have an external field that does work on the system through some coupling, okay, with the degrees of freedom of the system. And there is what is called the deterministic thermostat, which is a term that subtracts the extra energy given to the system by the external field so that the system can stay in a stationary state. And one then can compute from the evolution of this system various quantities which are of physical interest through the rules of statistical mechanics. In particular, in this case, one is interested in what is called the dissipative field, which is related to the entropy production when we are close to equilibrium and entropy makes sense, okay, to the dissipation of energy when we are in any other situation in which thermodynamics doesn't directly apply. And this quantity is defined by looking at the internal energy of the system. This would be the potential energy, is the kinetic energy. And it's adiabatic derivative, meaning the time derivative of what this quantity would be if the thermostat was not there, if the system was isolated from the system. So if the system was isolated, the field would increase its internal energy. Okay? If you remove that energy, say because you dissipate heat, then okay, you define this thing. Okay? V is the volume of the system. And this, yes, this apart from the fact that it's not divided by kBt, this would be the entropy production. In this form, it's just energy dissipated in the system because there is a field working and the thermostat absorbing the extra heat. Now, the story that I want to tell you starts with a paper by Evans, Cohen and Morris dated 20 years ago. It was for one of the systems that I showed you, a particular one called SLOD for a strange reason, isoenergetic, meaning that there is a thermostat which takes this form, which works in such a way to keep constant the internal energy of the system. Okay, and what does this represents? Well, gamma is the shear rate. It is a particle system that simulates a fluid being sheared at that rate, gamma. Okay, now this is the notation of that paper, which was a physical review letters paper, and I'll later switch to a simplified, more general notation. Okay, but this, for historical reasons, I wanted to show to you this. So these are the equations of motion. What I didn't say is that this kind of equations of motion are time reversal invariant. Okay, so one can ask questions about if I see a certain property which is odd with respect to time reversal, if I see taking a certain positive value A, whether I can observe the opposite value as well. The dynamics should allow. The question is the probability. So they ask precisely this question. They ask, what is the probability of observing along a trajectory segment I in phase space, of observing a certain positive value of the entropy production compared to observing trajectory segments of opposite entropy production for a time tau. Okay? And they try to use say an expression for the SRB measure, assuming that this system might be of that kind. Okay? An expression which links these probabilities to the finite time Lyapunov exponents, positive ones, okay, computed along these trajectory segments. And if you use the time symmetry that you have in this system, what you would find is that the negative of the sum of the positive exponents of the trajectories that produce a negative entropy production is the negative of the negative exponents of the trajectories that produce a positive entropy production. So in here, what you get from this ratio is the full phase space volume contraction rate, which in this system happens to be connected to this quantity here, the deterministic thermostat, okay? Because the deterministic thermostat in this particular kind of model is proportional to the sum of all the Lyapunov exponents that you compute along one trajectory, and that happens to be proportional to the entropy production rate, because in this system, this is the entropy production rate. Now, in particular, this pxy would have been the off-diagonal component of the stress tensor, okay? But we don't need to dwell too much on this. This relation was considered important. A number of papers were written after that on this, because it was interpreted. Now, this would be a long story. I don't want to enter into that, but it was interpreted as a quantification of the second law of thermodynamics for a time reversible system, which had not been done before. Okay, now, whether that interpretation was right or wrong, in any case, it induced a lot of discussion and works. Okay, it is important for what follows to keep in mind this, that the isoenergetic constraint, which requires a thermostat alpha of this special form, is the reason for having what is the entropy production being proportional to the phase space rate of contraction of volumes. Okay, this is what I just said. The model was chosen because the phase space volumes contraction for this particular time reversible model can be related to the SRB measures through the variation of volumes in the phase space. Okay, and this idea was made explicit in Gallavotti-Cohen in '95, and from that a lot of works came in and gave rise to what I call quite nice mathematical theory, which can be made rigorous thanks to the machinery available for Anosov systems. Very elegant. For instance, here I see David Ruel and his paper of '99 really makes it very elegant. Okay, what I have shown to you. But it proved to be hard to advance, and it also, from a physical point of view, and it also faced a certain number of conceptual and practical difficulties. Now, for those who are familiar with the stuff, maybe this will be clearer, but the idea is this, is that from a physical point of view, considering as a variable of interest, the phase space contraction rate runs into problems around equilibrium states, in particular for what concerns the time scales. Okay, the mathematical theory has to be all asymptotic in time, so the time scales are a little lost. But if one does explicit calculations, there are problems here. There are problems because the phase space contraction rate is not associated with energy dissipation, except in these very limited isoenergetic cases, which for a non-equilibrium system are also quite awkward, okay, because I would have to think of a system that is being driven by some external agent. At the same time, it keeps constant its internal energy, which is not easy to see. Okay. Nevertheless, a lot of people verified numerically and experimentally the validity of that relation, which is called the fluctuation relation, for the quantity which is physically observable, which is the energy dissipation. Okay? And so the question arises as to how can one reconcile these observations with a theory of steady states of reversible dissipative systems. Okay, the reversibility is in the equations of motion. The dissipation leads to some kind of singular invariant measure in the proper phase space. Okay. So with the collaborators, which I didn't mention at the beginning, went too quick. Evans, Dennis Evans, Debra Searles, Owen Jepps, some postdocs and PhD students of mine and so on. We have tried to change the point of view and say this: if the fluctuation relation for a certain quantity is verified can we identify the mechanisms that are responsible for that? It is a different approach, because here, rather than inferring the fluctuation relation from the dynamical properties of the dynamics that one has, I say the fluctuation relation holds. Can I see what are how can that be possible? Okay, so this would be a search for necessary, not for the sufficient conditions, and for the physical structure, okay, because in some sense I will follow the path that is commonly followed in experiments, okay, and so I will be able to say a few things that in some sense surely happen when we do these measurements in physics, okay. So now let's make this a little more formal, and I will consider a dynamical system in a certain phase space M. This will be my evolution from a given initial condition, which, I always have in mind is of this form. I will say that the dynamics are time reversal invariant, meaning that there is a time involution that anti-commutes with the time evolution, but dissipative, meaning that in the steady state, according to the invariant measure which we would have to qualify, the average of the divergence of the vector field is less than 0. Now, I'm going to endow the phase space M with an initial distribution which has got a density F0. And with this F0, I'm going to define what would look a strange function, omega naught. Okay? It is called the dissipation function. This is just for notation. By this indices here, I mean the integral of omega naught along a trajectory which has initial condition in gamma integrated between t and t plus tau. The naught is to recall that we are using f naught for its definition. Okay, so it gives you this. Lambda minus lambda is the phase space contraction rate. So it appears here. Okay, there is the logarithm of the values of the probability density that I have chosen at the beginning and at the end of my integration. Okay, so they play the role of boundary terms, which could be quite important with respect to this. Okay? Now, does this quantity mean anything?
Sorry,
please.
How do you construct omega 0? I mean, like...
I'm going to show it. Omega 0. Omega 0 is defined by this, okay? G is the vector field. The probability density is given. This is the initial state. You can think it is the initial state of your system. It's the initial ensemble. Okay? But indeed, here is what I have in mind. What I have in mind is this, is that for some miracle, which I haven't completely clarified so far, if by f naught I take an equilibrium ensemble, which one? The equilibrium state that I would have if I keep my system subjected to the same constraints that I have when it is evolving, but I remove the driving, so there is no dissipation, so it will be an equilibrium state. If I take that, then omega naught happens to be the energy dissipation rate. At least for the systems that I have studied so far, which are of the form, pretty general form that I've shown before. Okay, this can be seen. What did I do? In some of my papers that I can show you later. Okay, so this is indeed a funny definition. It came about in order to obtain the relation. Okay, there wasn't a particular interest in this omega naught. Later it was realized that it was the key to a number of things, which are the subject, the object of this talk. Okay? Funny thing, but if I choose a proper f naught, which by some miracle is the most appropriate one, because it is the equilibrium distribution for a system that is at time zero is being driven outside of equilibrium, okay, then it is the quantity of interest. This omega is odd with respect to the involution I. And if I consider isoenergetic cases of the kind that I showed you before, then omega integrated, okay, between time t and time plus tau. I will always use this integrated form of omega, so we don't need the local definition, is indeed the phase space contraction rate minus lambda. Lambda is the phase space variation rate, okay? So in the isoenergetic case, we fall back into what we Evans, Cohen, and Morris had considered, and then it was considered in the framework of an-on-source systems. Okay. But if the dynamics are not isoenergetic, and here I give you a case in which rather than fixing the internal energy, I fix the kinetic energy. Okay, the lambda, you see, that contains, besides the dissipation, contains some extra terms which could be divergent, and they are the reason why, if you want to investigate the properties of lambda, you run into some troubles. Okay, this may be unbounded. Okay, but if rather than using lambda, I use omega, knowing that this is the correct equilibrium ensemble. Okay, my omega again is precisely, apart from a proportionality constant, the energy dissipation. Okay, and I could go on with this kind of examples. So what happens is that not having to deal with this disturbing terms, okay, for instance, in this case, this is the interaction potential among particles. That's why it is unbounded. Okay, particles could interact with Lennard-Jones potentials, which have diverge at zero, distance zero. Okay, if you don't have to deal with this, you get a quantity which is much more easily treated because it doesn't have too bad a behavior. In any case, it is the physically observable one. So, the question now is what I do with this omega. And the first observation is this. Let me consider two intervals of real numbers, one centered on A plus delta, the other one centered on minus A. And I want to know what is the set of initial conditions gamma that give you an omega integrated between 0 and tau close to A. Okay? This set, by simple construction, is the set of initial conditions that give you an omega close to plus A, evolved forward for a time tau, and then you apply the involution. Okay? So if starting from this initial condition, going forward in time, you integrate omega and you get A. If I start from this initial condition and go forward in time, I integrate and I get minus A. So if I want to know the probability of these initial conditions with respect to the initial ensemble, which is this, I only have to integrate my density over these two sets. But these two sets are very simply related by this transformation, so I can transform the coordinates of the integral in the denominator in this way, introduce the Jacobian of the coordinate transformation, which is just the volume variation in phase space. Plug it inside here, you get this. Now use the definition of omega, it becomes this. This is already now an integral over the set of quantities that produce plus A. You integrate this you replace this expression using the definition of omega, you get this one. Okay, you get this one. So you have an integral of f naught times the exponential of omega in the set in which this quantity gives you something close to a. So you take this out of the integral, you have an error which is smaller than delta, okay? And this is the same integral that you have in the numerator of your relation. So you obtain this. Now this looks like the fluctuation relation I showed you at the beginning, okay, which gives an exponential say ratio between the probability of observing a positive dissipation A to a negative dissipation A. It is, this is really a very big number because tau would be the observation times, which in microscopic terms is a big number. This A is also the energy dissipation, so it is again proportional to the number of particles, so it is a very large number. So clearly, the negative dissipations are unlikely, exceedingly unlikely, even if the system is time reversal invariant. But in reality, okay, this is not the fluctuation relation we are speaking about, because you see, we are using this non-invariant probability measure, okay, which we have selected at the beginning in order to define omega itself. Okay? So this has been called the transient fluctuation relation for the observable omega. This relation is completely trivial, as you have seen. It's just the result of coordinate transformation for a time reversible system. Okay? But for that reason, it is an unbreakable identity. It is a property of this initial ensemble F naught, okay, which holds for all tau. It is exact. There are no approximations. Here, you see epsilon is smaller than delta, so at least I can make it as small as I like. Basically, it only rests on two ingredients: the time reversibility of the dynamics and the symmetry of the equilibrium ensemble itself with respect to the exchange of velocities. Okay, here I can get rid of this I because F naught is symmetric, which I didn't say. Okay, so it is trivial, but it's very robust. And to begin with, it is useful because it points out the role of this quantity omega. Now, I'm going to show to you that it turns out in many circumstances. In the first place, what I did in the previous calculation was to use the definition of omega to replace the phase space contraction rate and an evolving trajectory in the probability density, which makes very difficult to use the thing. And here I can do the same. If I want to know what the probability distribution would be at time t, at point gamma, okay, it's just this. Omega integrated from a previous time minus t, okay, up to 0. Okay. If I take another observable which is also odd with respect to the time reversal, then I obtain other transient relations of this form. This is useful because, you see, here I have one observable and here I have another one. Maybe one of these two observables is accessible, experimentally accessible, the other one is not. For instance, I have a concrete example. I collaborate with a group of people who try to catch gravitational waves, which is quite hard to do, and indeed no gravitational waves have been caught so far. But they're interested about the dissipation, but they cannot measure the dissipation because the gravitational antenna is a big bar in a fridge at the liquid helium temperature. So they can only measure currents, which are being amplified through complicated electronic devices. Okay, and so from an observable quantity which is not of interest, they would like to get some information on the observable quantity. Okay? So this again is an identity, is a trivial one, like the previous ones. Here the notation means exponential of minus omega integrated from 0 to tau averaged with respect to the initial distribution f naught under the condition that O, our observable, the visible one, our observable, takes an average close to A. Okay? And this can be developed into this. This is quite useful relation, keep it in mind. Again, it's direct consequence of this one. And it just expresses the conservation of probabilities in phase space. Nothing more than this, but it happens to be useful. Yes, why am I dwelling on this kind of trivial relations? Because they do something useful for us. I mentioned something, okay? Here I can say more. What do represent the various initial conditions of which I do the statistics? They represent different experiments that I can do, starting always from the same state, which is an equilibrium state. Okay? And by running a non-equilibrium experiment, the non-equilibrium dynamics, I can extract some information about the structure of F naught, which could be unknown. Okay? And so I do the opposite path of what the fluctuation dissipation relation does. In a sense, I close the circle. Fluctuation dissipation relation tells me about non-equilibrium properties by doing an equilibrium experiment. I can compute the viscosity of a fluid by looking at the motion of pollen in this fluid and doing no work. But the viscosity is something that will be manifested in a non-equilibrium experiment. Okay? So this is what fluctuation dissipation does. This kind of fluctuation relations, transient fluctuation relations, do the opposite. I do a non-equilibrium experiment to extract information on the equilibrium properties of the system. So it complements this thing. And this idea is widely used recently. You will have heard of Jarzynski relations and this sort. There is a number of these relations which do precisely so. They do non-equilibrium work in order to obtain properties of the equilibrium state. So they have been verified experimentally. And because they are unbreakable, as I said before, one can trust them. And Dennis Evans, who is at the beginning of this story, okay, he trusts his calculations much more than I would, but often he happens to be right. So let me tell you this nice story. They wanted to test in an experiment of colloidal particles in water dragged by optical tweezers. They wanted to test this relation here. And they wouldn't get one, they would get 10,000. So he was mad at the people in his lab, saying that they can't do experiments and all these sorts of things. And he pushed them and pushed them until what they found out was that in the experimental equipment, the lubricant of the barrel which holds the microscope was actually deteriorating in time and setting the microscope out of focus and then giving you wrong results. This was then communicated to the factory producing this microscope, which I think is Zeiss. And so they could fix it. And after they fixed that, okay, the relation was verified. I must confess that I was telling him, Dennis, look, it means that this relation doesn't apply to this experiment. He wouldn't listen, and he was right. Okay, but now let's go back to what were the steady state fluctuation relations. So the probability distributions in the steady state, in which I use an invariant probability rather than the one that I have constructed at the beginning. Okay? What should I do? What should I do? So typically, I cannot start an experiment in the steady state. Okay? For instance, the light coming from that lamp up there is in a kind of steady state. But how does it reach the steady state? Well, first when the switch is switched off, there is no light. And the neon there is in equilibrium state. The gas flowing through is in an equilibrium state. Then you switch on the electric current, and it moves to the steady state that we see. This is typically what you do. You cannot start an experiment straight in the steady state. Typically, you start from an equilibrium state. Okay? So this is what we have done so far. We started in an equilibrium state, and then we switch on at time zero the driving. Now the answer we want to ask is whether this evolving probability driven by the dynamics, which is dissipative, okay? What the statistics will look like after a time t, hoping that if I let the time t go to infinity, I will get the answer above the steady state. Okay? Hoping that this mu t in time reaches a steady state. Okay? So I want to know about these ratios of probabilities now. Not about the ratio of probabilities with respect to the initial ensemble, but with respect to the evolved ensemble up to time t. And you just use conservation of probabilities, which says that this ratio is equal to this ratio, still can be related back to the initial probability distribution that you knew because you constructed it. Okay? So again, we have to ask the question, what is the set of points in phase space that produces something minus a compared to the set of points that produce plus a? Now here look that we want to know an observable integrated from time 0 to time tau. Okay, but when we do this transformation, we get the observable integrated from time t to time t plus tau. Okay, it's quite obvious. So what you do, let's say that this is the initial condition of a phase space trajectory that will produce an integral of omega close to a after a time t, meaning in this section. Okay? If you want to get, thanks to the reversibility of the dynamics, the initial condition that will produce minus a after a time t, what you have to do is you wait for a time t, do your job, continue for another time t, and now here do the time reversal operation that takes you down here. So now here you have an initial condition that you wait for a time t. It produces minus a in the subsequent time tau. Okay? So the set of points which is relevant in this denominator now is obtained from the set of points which is relevant in the numerator this way. Okay? These are the initial conditions that give you something close to a. Evolve them for a time t plus tau plus t and then do the time reversal. And you get this. So this is now the new coordinate transformation that you have to do in order to compute this ratio. Well, we'll better take the logarithm and divide by tau for the reason that we are going to see. Now this is still an identity. This is still an identity, although here I have now the probabilities at time t. Okay? And here you recognize the three pieces of the trajectory. Before we observe omega, during the observation time, and after. Okay, this is the conditional average of this quantity with respect to the initial ensemble, the equilibrium one which we know, under the condition that omega in the observation time has an average close to a. So this bit can be taken out of the integrals as we did before, because this bit takes a value close to a with an error epsilon which is smaller than delta, and this is what you are left with. Now this is the really interesting part, is this kind of correlation term, okay, computed with respect not to the invariant distribution, but to the initial one. Okay? Well, it's a conditional average. Okay. Now, we want to take the time t to infinity, hoping that that will take our mu t to the mu invariant mu infinity. But if we take t to infinity without any assumption, you remember that this is an integral of a quantity, the dissipation, okay, which is macroscopic, and in a long time it is bound to be positive in general, so this integral will diverge when t goes to infinity, and it appears here. Okay? Then this whole thing may diverge or go to zero, which with the logarithm is the same. Okay? So if this object diverges, then this relation doesn't, this ratio of probabilities here doesn't make any sense. Okay? We do not have a fluctuation relation. Fluctuation relation would be this left-hand side equal to this bit, maybe with a correction that we can kill by taking tau large. But if this diverges, there is no limit in tau that you can do. Okay? Well, this is still an exact identity, so it is not strange that you have pathological situations. For instance, there are systems which have no fluctuations in the steady state, and then you cannot have a fluctuation relation for them. Okay? But let's say that this quantity does not get out of control. Okay? Then what we would have is indeed steady state fluctuation relation in an ensemble sense. Okay? Steady state fluctuation relation with a correction of order 1 on tau for the dissipation function. Okay? So, if I know that the fluctuation relation holds in the steady state, and that my experiment started in an equilibrium state, this must have happened. This thing has not got out of control, at least for some values a. And the question is, what does it mean to require that this remains bounded? So I said, let's consider the case of instantaneous correlations with the distribution f naught. Okay? What we have is this quantity. The product of these two terms under the condition which concerns times in between these two. And these two are separated by time tau, which could be large. So let's say that the conditioning is not relevant. In this sense, I intend decay instantaneously. So the conditional average is equal to the full average. Then this term here is just this, okay, evolved for a time t plus tau. So I could further say that this factorizes. And if this factorizes, that was the relation, okay, that Dennis Evans wanted to test experimentally in his lab. This is 1. So what I'm going to do in my slide here is to plug 1 in here. Logarithm of 1 is 0. So I get for every tau that the relation left-hand side equal to this cut at A is valid. Okay? But in general, this may be too much to ask. Also, I don't know precisely what it means. But if the object remains bounded, and it has if I have verified the fluctuation relation, then I know that I have a correction of order 1 on tau. But then this suggests one notion of mixing, which is not the one concerning the invariant distribution, but my initial equilibrium distribution. So let's say that we have something like this, okay, where P and O are the observables we should be better qualified, but let's take them like this for the moment, okay? By this I always mean averaging with respect to the initial expectations with respect to the initial F naught. And then let me say that one of these, the P, is omega itself. Then omega is odd. The distribution is even, so this average is 0. So this condition amounts to asking that this thing goes to 0. We decided to call T-mixing the condition in which the integral of this quantity from 0 to infinity, okay, is finite. It simply means that this kind of mixing condition with respect to the quantity omega implies a decay of this quantity faster than 1 on t. Okay, that's all. Why do we want this condition? Well, in the first place, okay, it is a generalized requirement, okay, with respect to what we needed to obtain the fluctuation relation. But there is more, and the more is here. Just algebra, pure algebra, and the definition of omega shows that the derivative of the average of O computed with the evolved distribution at time t is equal to this quantity. Okay. This has some implications. Okay. For instance, you can get this derivative of the omega itself at time 0 is bigger or equal than 0 and equal only if you are in the equilibrium state for which omega is 0. But then this can be integrated and gives you the response formula. The average of O at time t is the average of O at time 0 plus the integral of this quantity, which should go to 0. And if it goes sufficiently fast, the case that we call T-mixing, that it means that the response, okay, amounts to a convergence to some, I say ensemble, steady state, because from what we have imposed, I cannot say precisely, okay, whether this is a single steady state, or there is a splitting, okay, where half of the phase space is attracted by one attractor, other half by another attractor, or many more, and so on. Okay, but this is just an identity, unbreakable, as the ones that we had at the beginning. Okay, and if there is a unique attractor at the end, then this also means that for a single system, I would see convergence to the steady state. Otherwise, I can speak about the ensemble of experiments that I'm speaking about. It works also for convergence. Yes, it was always hidden in my mind that the dynamics would be dissipative, but that don't need to be. Don't need to be. So again, I would like to know what is this T-mixing condition? At least in physical terms, I don't know. What we are saying is that correlations computed with respect to this F naught Okay, correlations of whatever observables with the dissipation function decay sufficiently fast. Means that decay sufficiently fast with respect to the initial macro state. So it is something that is needed to forget the initial macro state. So if I want a condition, a necessary condition for reaching a steady state, this condition has to be satisfied. Okay? Obviously, it is quite different from the standard mixing condition, which concerns the invariant measure, so I'm already in the steady state. So this seems to be a loss of memory between macro states, while the standard mixing is the correlation of microscopic states, and so it cannot tell us about the convergence in a steady state. The important thing is to keep in mind that experimentally, this is what we do. We start from an equilibrium state and then let things evolve. So this theory mimics what one would do in an experiment. Yeah, I think I'm about to finish. Yes. And I'll summarize what I have said in words to recap. Perhaps I could have been a little slower, but we summarize things now. Okay, so we have seen that fluctuation relations were proposed for systems in non-equilibrium steady states 20 years ago. Okay, they appear to be important because they were parameter-free. From an experimental point of view, this is important. They make prediction that doesn't rely on parameters that you have to fix ad hoc in order to get your result. So they appear quite universal. Because they are based on dynamics of systems that are generically dissipative, then they can extend beyond the standard thermodynamic theory of non-equilibrium systems, which is the one based on local equilibrium. Okay? Here, thermodynamics may fail, and still these relations hold. Okay? And so they seem to be relevant for systems in non-equilibrium conditions where the non-equilibrium, the thermodynamic equilibrium can be violated for different reasons. Okay? Because the driving is too strong, or also because the system is small. And because we speak of fluctuations, the fact that systems are small small systems is where they seem to be more promising for applications. Then we have seen the transient fluctuation relations. The transient fluctuation relations don't speak of the statistics of a single system, but of an ensemble of systems, an ensemble of experiments. But they are so trivial that are impossible to break, as long as one believes that the microscopic dynamics should be time reversal invariant. Okay, and they pair quite well with the fluctuation dissipation relations. They go beyond that, okay, but they do the opposite in the sense that they can give you equilibrium properties, for instance, free energies of molecules in some liquid by doing some non-equilibrium work. And their merit is to point out that in order to get a steady state fluctuation relation, one needs to introduce a certain condition. Now, this condition is imposed on us. It's not that we want it to have. If the steady state fluctuation relation, we have to have something of this sort to be verified, and that seems to amount to a decay of macroscopic correlations, which then gives us also a way of thinking about convergence to a steady state. All the relations, I haven't shown you all what can be obtained in terms of omega, okay? there are identities, inequalities, the response formula that I showed you. Okay, they rest on this so far relatively mysterious quantity omega, which in specific systems is precisely the energy dissipation, so it is the quantity that can be experimentally measured. And in particular, the response formula is a generalization of Green-Kubo, not only because it applies further away from equilibrium, okay, but even close to equilibrium, where Green-Kubo would apply, it is more general and easier to use, because if I go back, this looks very much like a Green-Kubo relation. But the difference is that in Green-Kubo, if I give a certain perturbation, I can look at the response of a certain observable. Okay, so the two things are tightly connected. In here, whatever observable I take, I'm always going to use omega. Okay, so I think that this is really the end. Thank you to all those who survived so long.
Questions?
Just a comment. So somehow, let's try to see the procedure by which you construct this thing. So basically, let's say you are in a non-dissipative system, and then at a certain time you add something which will make the system forced and dissipative. So somehow you switch on at the same time forcing and dissipation, right? Okay. So somehow, I mean, also the final result you get. I mean, this is. I mean, in the work with Matteo has done together with me recently, and just submitted in archive with Journal Statistical Mechanics. We get exactly the same result, but with a different point of view. So basically, we assume that our system has an absolutely continuous invariant measure at the initial state, which is well compatible with being with equilibrium, say. Then you switch, you make a perturbation which might well take you out of equilibrium. Then omega 0 appears when you do the integration by part to the basically to get the fluctuation dissipation result. So we get exactly the same, but we are looking at it from a different point of view. So we were looking at it from the point of view of the properties of the invariant measure. So somehow this would be the experimental procedure to realize this sort of response somehow, I think. So and we get exactly the same omega 0. So we have the sum of two terms. The second one is the divergence of the phase space, and the first one is in fact the other part, which would be the force, some sort of energy. The sum of the two gives the energy dissipation. So it's a very different procedure, but we get the same result, in fact, in this last formula. So it's quite
I think so. I think that there are some other approaches that come close to give what formally looks the same result. I think we need some work to distinguish the differences and the analogies. Okay, here the important thing is that omega is not a mathematically useful quantity, but is the real energy dissipation in the system. And that which is connected to the equilibrium ensemble the way that I said. So I don't see difficult. I don't find difficult to believe that in other settings you get the same thing, and you could make this say purely formal and forget about the equations of motion that I had in mind and so on, and just do the formal calculations that I did. Then F naught has only to be, in my case, a quantity which is even with respect to the time reversal involution.
Yeah. So I mean, I think that if we put our result in the Hamiltonian setting, so if we put the physics, it's exactly the same, and the expectation value of omega 0 in zero is zero, in fact, right? Which says
because because
so
it's just
because you say
this is odd and the ensemble is even.
Or you can say in the equilibrium, I mean, in an even more macroscopic term, if you are in the equilibrium, no energy is being dissipated. Otherwise, you could not be at equilibrium. And so somehow this T, I'm trying to connect. This T mixing is like saying in the language of response theory, saying that you can resum the response. Somehow you are able to do the time integral. So here you look at it as from the properties of the trajectory, and but it's actually it's a quite I think clear connection. It's quite good.
Yes, I agree. Let me just show you the definition again, which is interesting on this, which is this. Okay, now you know that in the what they call stochastic thermodynamics these days, okay, developed by Van der Broek, Esposito, okay, and number of people. Okay, there is something similar of this sort. If we go back to the works of Leibowitz and Spohn, this would be the boundary terms that they could do without for when trying to get the fluctuation relation for a Markov chain, okay, because they were using bounded state space. When the state space is not bounded, you need this to obtain the right thing. What I think is that in the case of equations of motion which are explicit like this, okay, then you know that that quantity is the energy dissipation. In other cases, like the stochastic ones and so on, you choose the quantity that does the right thing. Like Leibowitz and Spohn honestly say in their paper, they say, well, what would be the entropy production in here? No clear idea, but this works. Here is not so much that thing is that you can say, yes, this is the right thing. Right? This is the energy dissipation because you have a specific model. Formally, you just evolve probabilities.
Okay. Thank you very much.
Thank you.